Well, welcome back. This is the appendix on the hexadecimal number system. First of all, let's talk about why we would need to use yet another number system, the hexadecimal number system. Humans have been using the decimal number system for a long time, and now we have computers that use the binary number system. One more number system, and it's used to help us represent the numbers that are internally represented as binary. So if you look at this binary number with all these ones and zeros, this is not something that you would want to write down and try and figure out what this means. You wouldn't call someone up and read this number to them on the phone. They couldn't possibly write it down. So we need a more human way of representing these binary numbers. And it'll come clear to you why we've chosen the hexadecimal number system, because of the conversion between binary and hexadecimal. So the computers are working in binary, and we need an easier way to look at these binary numbers, a more human way. That's why we've chosen the hexadecimal number system. Well, hexadecimal, or sometimes we'll just call this hex, is base 16. In the previous appendix, we compared base 10, the decimal number system that we've been using all our lives, and base 2, or the binary number system. In base 16, or the hex number system, we have 16 symbols to work with. Similarly, in decimal we had 10 symbols, and in base 2 we had 2 symbols. So there aren't 16 different digits that we can use as symbols in the hex number system, so we've borrowed letters, and we're going to use the letters A through F to represent the values 10 through 15. So the hex number system, base 16, uses these 16 symbols, 0 through F, and a good way to start working in hex and getting a feel for it is to just go to a spreadsheet and start to count in hex and count along with the other decimal, the other number systems, decimal and binary. So let's go do that now. One of the best ways to get started thinking about hexadecimal is to just look at some numbers as we count in the different number systems. So here is in the third column, counting in decimal, which is what we've been doing since we were children, 0 through 15. And if we compare that to counting in binary, 0 is the same in all number systems. And then in binary, 1 is the same in all number systems, actually. And then in binary, to represent 2, you need to have 2 places, 1, 0, and so on. When we reach 10, something different happens in hex. We still want to represent 10 in one hex place, but we don't have a symbol for that, so we introduce letters as well. So in hexadecimal, the character A, the symbol A, is going to represent 10, and so on up until F is going to represent the value 15. So when we go to 16, in binary, we need one more place. So we would say 1, 0, 0, 0, 0. We have 5 binary places now to represent 16. In decimal, of course, 16 is 16. And in hex, we have 1 group of 16 and 0 groups of 1. So how would we represent 17? In decimal, it's 17. In binary, 1 group of 16 and 1 group of 1. And in hex, 1 group of 16 and 1 group of 1. So here's what's happened in hex. We have 16 different symbols because it's base 16. And we've added the symbols A through F. The reason that we use hex is because 4 binary places translate into 1 hex place. So it isn't a coincidence that 1111 is the largest value we can represent in 4 bits, and that's also the largest value we can represent in 1 hex place, which is the character F. Okay, as we continue to look at the hexadecimal number system, or base 16, let's go back and review the base 10 and base 2. So in base 10, we started out by looking at a regular decimal number, 983, and we explored that that's the same as 9 times 10 to the power of 2, or 9 hundreds, 8 times 10 to the 1, or 8 tens, 80, and 3 times 10 to the 0, or 3 ones. So 983, this is the number system that we're used to using all our lives. 983 is 9 hundreds, 8 tens, and 3 ones. In binary, which is base 2, we had an example number 1101. We looked at what that meant. The first one, the most significant one, is 1 times 2 to the power of 3. 2 cubed is 8. So 1 group of 8, 1 group of 4, 1 group of 0 groups of 2, and 1 group of 1. So if we add these up, 1101 in binary turned out to be the equivalent in decimal of the number 13. In hexadecimal, or base 13, base 16, we're going to use our powers of 16 to determine the value of the places. So 16 to the 0 is 1, 16 to the 1 is 16, 16 squared is 256, and 16 cubed is 4096. So we have a 1's place, as we have in all number systems, a 16's place, a 256's place, and a 4096's place. These get very large very fast in base 16. So have a look at this example number in hex, 3F8. Let's explore what that means. When you write a number in hex, we typically will write 0x at the first of it so that we can tell that it's a hex number. So that's what that 0x is there for. It doesn't represent anything to do with the value itself, which is 3F8. So let's take this number apart. We have 8 groups of 1, which is 8. And then in the 16's place, we have an F. So we decided that F would be, look over here at this legend, F is 15. So we have 15 groups of 16, and if you multiply that out, you get 240. And the 3 represents 3 groups of 256, which multiplied out is 768. So if we add these up, we find out that 3F8 in hex is the equivalent of 1016 in the decimal number system. This is the one that's the most new to you, and the one that takes a little while to think about, because we have these extra characters, A through F, that we use in hex. So in each place, in hex place, each hex place, you can have the value 0 through 15. And these represent groups of, or how many will be, in powers of 16. So 8 ones, F16s, and 3 256s. Okay, now we're going to talk about converting between hex number system and the binary number system. So let's start out with this number that we worked with in the previous segment, the 3F8, which is a hex number, and we're going to convert this into binary. And let's look at the 8 first. Each hex place can represent 4 binary bits. So the number 8 in hex is 1000 in binary. So let's write 1000 here. The F represents in binary 1111, and the 3 in binary, in hex, sorry, is this bit pattern 0011. And those leading zeros are not meaningful. It's just a little bit easier to sometimes look at 4 bits at a time. So here's the binary equivalent of this hex number. Now this is much, much easier than the conversion between hex and decimal. And the only reason that we use hex at all is because of this nice translation between hex and binary. So recall that what we want to do is to think about these binary numbers, which are represented in the computer, in your variables, in C for example, and we want to look at these values in a way that's more human to us. So instead of saying 11, 1111, 1000, we can say 3F8 and know that we have this bit pattern which is represented by this hex value 3F8. Now if we wanted to convert this binary number into decimal, or this hex number into decimal, let's do both of those just for practice. Well, 3F8 we did in the last slide. 3 groups of 256, F groups or 15 groups of 16, and 8 groups of 1, which is simply 8, and when we add those up we get 1016. So here's how we would do a conversion between hex and decimal, and I skipped through some of this. I didn't do all of the multiplying and the addition because we had just done it before, but that takes much longer than it took us to do the translation between hex and binary, because each of these excuse me, hex places represents 4 bits in the resultant binary number. So just because I wrote all of these bits in separate blocks here in this spreadsheet, that doesn't mean we have 3 different binary numbers. This is one binary value, which is the corresponding value to 3F8 in the hex number system. Well, when we get numbers that are this big, doing the conversion by hand starts to be quite tedious. So let's go and have a look at the calculator and make sure that we're doing this correctly. Do I have room for this? Well, let's put it here for now, and let's type in that binary number. When you click on binary here, we see that we have only 1 and 0 to work with. So we have 1 1 1 1 1 1 1 0 0 0, and if we convert that to decimal we have the value 1016, and when we convert it to hex we have 3F8. So using a calculator is much simpler than doing these out by hand, but it's important that you can do them by hand so that you have you can demonstrate a solid understanding of the concept of the number systems. Okay, while we're here, let's look at some special hex numbers. How about this one, 0xFF? Well, what would that value be in binary? F is 1111 and F is 1111. It turns out that this value, 8 ones, is the largest value that you can store in 1 byte. If we write the number 255, that's the decimal equivalent of turning on all of the bits in 1 byte. So 255 is kind of a magical value. For us, it's the largest value you can put in 1 byte, and it also represents is also represented as FF in hex. So we could talk about 255, and that's just kind of looks like a random number that doesn't have anything to do with binary. Or we can say, hey, look, it's all ones in a byte. Or we can express it more simply as FF in hex number system. So what would be the largest value that you could store in 2 bytes? So if we had 2 bytes of memory, we could write 0x FF. Let's turn on all of the bits in 2 bytes. 1111, 1111, 1111, 1111. So if we have a variable in our language, our C language for example, a variable that takes 2 bytes of memory, and we want to set all of the values to 1, all of the bits to 1, we could either use the decimal number or the hex number. Now, what is that decimal number? It isn't obvious from this, and converting it would be really quite tedious as it starts to get longer. So let's go and bring up the calculator and say in hex we have FF, and convert that to decimal. And this is another one of the magic numbers in computing, 65,535. And this is the largest number that can be stored in 2 bytes of memory. So we have the range of values in 2 bytes of memory, 0 to 65,535. In 1 byte of memory, we would have the range of values 0 to 255. Similarly, let's throw that away for now. If we had a large binary number, 1011, 1100, 0011, and I want those leading zeros to stay there because they are significant digits in this number. That's better. And 1000. So now we have a binary value that takes 2 bytes of memory. We have 16 bits here. And we're going to convert that to a hex number. This is all one value, one big binary number. And when we convert it to hex, we can convert it 4 bits at a time. So let's do the least significant 4 bits first. 1000 is the value 8 in hex. So let's put an 8 there. 0011 is 1 and 1, 2, which is 3. 1100 is an 8 and a 4, which is 12, but in hex we're going to write C. And 1011 is an 8, a 4, and a 1, which is 13, but in hex we're going to write D. So this binary number is this hex number, and we would write it 0x DC38. This conversion between binary and hex is much easier than the conversion between binary and decimal, or backwards, the conversion between hex from hex to binary is much easier than going to decimal, and that's why we use hex, because of this 4 bits to 1 hex place relationship. What value is this in decimal? Well, I really don't know. DC38 in hex, I probably would use a calculator for that. So in hex, DC38, what number is that in decimal? 56,376. 56,376. Okay, what you should be able to do now is to take any number in hex and convert it to binary, and vice versa. Any binary number you should be able to convert to a hex number. You should also be able to convert between binary and decimal. So if you have a binary number and need to know what that decimal equivalent is, for small numbers you should be able to do this with a piece of paper, and with large numbers you should be able to do this with the converting calculator. I'm not sure if I just mentioned this or not, going from decimal to binary, binary to decimal, and going from binary to hex, and hex to binary. Those are the conversions that you should be able to demonstrate with small numbers on paper and with larger numbers using the calculator. Hey, did you notice a mistake in here? I converted 1, 0, 1, 1, and I got D, which is wrong. The correct answer, 1, 0, 1, 1, is B, and the answer here, the whole number, should be BC38 instead of DC38, which is a very different number. I decided to leave the error in and point it out to you because part of the objective of this segment is to convince you that working in binary numbers is very difficult for humans. And here's a visual aid that I created by mistake to convince you that working with numbers is really error prone, and if you were in the middle of a large problem and made that mistake, it could cost you several hours. So we don't want to be working with binary, we should be working with hex as much as we can. Okay, now that you've looked at the hexadecimal number system, you might want to test your knowledge of that by looking at these simple exercises. Convert these numbers from binary to hex and these hex numbers from hex to binary. If you can do these conversions and check them with a calculator and get them correct, then you have a grasp on what we need you to achieve in this appendix. Quick review of the concepts from this appendix then. We have the hexadecimal number system, commonly called hex, and it's base 16. Hex is used as an easier way to represent binary numbers. It's a more human way of looking at the values that are being manipulated by the machine. And every 4 bits of binary, every 4 binary bits are represented by 1 hex place. So this is what makes the conversion even of large numbers very easy. I think all programmers have to know how to represent numbers in binary and hex, and to understand how to convert between them and what the conversion is actually doing. So this is a required part of the course. It's not just because it's an appendix you look into it because you might find something interesting. It's a required part, and in most courses that are intro to programming concepts, this would be something like 10% of your grade. So 10% of all programming concepts are binary and hexadecimal number systems. Thanks for watching.